Yeah, less planes. Yeah. Hello. Hi. So, I've got another friend. Two. That's great. So we're going to start this afternoon with the Go Wi-Fi draw for light bulbs, but they're not everyday light bulbs. These are totally unhackable internet-connected light bulbs. you might be able to amplify something out of them. They probably run SNMP, so you can probably monitor them with multiple tools. So we just need someone to choose a random number, and the deal is if you're not in the room, you don't get it, right? I'm not sure if getting coffee counts as in the room, but I guess if you're in the room. We just need a random number, and I thought we'd just go for get the person to choose the number who's come the furthest, who I think is the guy from Russia, probably. Spain would be the furthest. The Italian. So the Italian would be the furthest. Where's one of our Italian contingent? Oh, there we go. So we need a number between 1 and
55.
55.
And this will be, should we do?
42. Ah, good number.
42. Robin Kong.
Kong?
Yeah.
Robin Kong? Do we have Robin? Redraw. Yep. I thought it was next speaker. Okay, redraw. So you choose a number, Rada. 33.
33.
I can't read it. My eyes don't work.
What's that? Florin Zyku?
Oh, Florin?
Yep.
Yeah, Florin. Florin is having a really good week. I was in the Facebook thing with him, and he won like programmable Lego as well. So you've had a good week. Yeah, good week. That's one person that's going to come back next year.
Okay, so this one here will be that was the LifeXZ strip. This is the main one, so you get 4 bulbs and the LifeX strip as well.
Okay, so why don't you choose a number, but not your number, obviously. 39.
39. Stephen Sheehan.
Oh, Stephen Sheehan. Stephen. You here, Stephen? Oh, Stephen. Oh, Stephen's been to every single NZNOG ever. And he's not here for his moment. Oh, okay. So someone else from far away, maybe.
Spain, maybe?
Yeah?
Let's say 12.
12.
Oh.
What was it?
Fraser.
Is that okay? Fraser?
Do we want to give him a second gift? He won the other one, didn't he? This is his lucky day. What does everyone else think?
I don't know. What do you... Fraser, what do you got? Okay, choose a number, Fraser, but not 12 or 33 or 42. 11.
11, okay. Oh, Ewan. Spike. Spike.
No one wants these light bulbs. This is crazy. Number one, okay.
Number 1. Who was number 1? Oh, Nigel. Nigel Ferguson.
Nigel Ferguson.
Hey!
Excellent. Cool. Okay. Excellent. So thank you very much. Thank you, Go Wi-Fi and Go Wireless, and obviously all our sponsors are very important, but we really love the ones that give away stuff. It's really cool. And speaking of giving away stuff, these glasses were found at the venue last night, so thank you. They're really nice. They're my colour. But if they do belong to anyone, they'll be just out the front. Cool. So, so now Daniel's got his big moment, and I know he's not nervous at all. So let's give him a big round of applause.
Okay, so welcome back from lunch, everybody. My name is Daniel Griggs, and I'm working for NZ today. And I'll be talking about accidental data analytics. I was running a little project to modernize our DNS charting systems. I wouldn't call it monitoring our DNS systems, but it's more of an instrumentation, although that might be a little bit generous. What we were using was DSC. Some people who run a name server may have seen this before. It's a common system that everybody uses. We have about a decade's worth of data in this, so we're not going to stop collecting DSC data. We just wanted something that looked a bit nicer and updated the data that we could collect. It became the new minimum, so we had to have something that was that and more. We did briefly think about using Hedgehog as the front end, which is a rewritten front end for DSC, but it didn't really add anything extra. It just looked a little bit nicer, but was way more complicated. What did we want over the top of that? So there was only a few little things I was looking for. And when I mean time travel, I wanted about a week's worth of raw data so that if I wanted to make up a new analytics or some sort of data lookup, I needed some historical data I could go back and see if that was going to be useful or it revealed anything useful. I wanted some nice looking charts because people who wear suits and ties and have corporate credit cards like that sort of thing. But more importantly, it needed to have a low complexity and a low hardware requirements. Because I was doing it as a side project, I couldn't buy any hardware for it. And I was doing it in my spare time, so I really didn't want to spend a bunch of time setting up Hadoop clusters or anything like that. And also, I didn't have the hardware for a Hadoop cluster either. Okay, so I'm going to skip to the end, skip to the start and show you the charts we ended up with. So I'll just run through these and then I'll get to the interesting stuff. I've grouped the dashboards by area of interest. So this is the clients we're looking at. So the top one there is the average number of requests they're seeing per client per minute. The next one down is the source port we're seeing, the source ports we're seeing as a heat map. So you can see there's a big bias towards 30,000. And every once in a while you see a little rash come up where we get a new client like harvesting or doing a bunch of bulk lookups, and they'll have a different bias for different port they'll be coming from. The next one down is the remaining TTL on packets that are coming in, and that allows us to see where there's been network changes. Perhaps the path becomes a bit longer, so the TTL becomes a bit smaller, or it becomes shorter. And so that's useful, and we can break that down per site, so that's pretty handy. And the next one is active ASNs we're seeing as well. And we can, again, break that down by site, so we can see how many ASNs are getting serviced per site. There's still... It's going to be prizes. Okay. The next group is the queries we're getting and the data around those queries. So the resource record types, the flags we're seeing coming in on the queries. If I take away the top 13 type of resource records, or the most popular resource records, the less popular resource records are graphed. Otherwise, you just don't see them. They're a rounding error in the graphs. And the opcodes we're seeing in the queries, which is pretty standard and kind of expected to see that. And the replies. We would be expecting to have matching resource records in the replies, so that top graph should be the same as the previous graph. The reply codes we're sending back, whether or not it's NX domain or they've actually found a useful domain. Are the flags, which is pretty boring. And then we've got the per site latency, and I'm showing a 50th and 95th percentile with a 5 percentile band on either side of it. So it's useful for viewing the reply latency we're sending back directly out of our sites. We can see any changes, and you can see those changes highlighted there. The next one is the volumes we're getting. Don't worry, there's not many more of these. The per site traffic we're seeing, the average domain length we're seeing, and you can see there's quite a bit of inter-site variation of the domain length queries we're seeing, which shouldn't vary, but it's a pretty interesting stat and something that asks more questions than it answers. The reply size heat map, which isn't particularly useful because everything kind of sits down below 1,000 bytes in size, although we do get sometimes those larger replies which kind of give you that striated look to it. And the last one is the average reply packet size we're seeing. And this one's for the NOC screen. Everyone likes a big world map with big round circles on it. So that's the volumes of traffic we're seeing from each country, broken down by country. And then the top 6 ASNs we're seeing traffic from as well. And you can see the patterns change as different hosting providers have different clients connecting and doing, spinning up different tasks. Okay. And also it's black because it looks tactical. So what was the tooling to achieve all this? I'll just quickly run through that. Parallel, if you haven't seen Parallel as a command line tool for operating over a bunch of files in parallel over a file system, it's brilliant. It automatically detects how many CPUs you've got and just runs stuff in parallel. It saves me the hassle of trying to figure out how to run tasks in parallel. It just does it for you. If you can use Xargs, you can use this. And SEM is also a super useful one if you've got a bunch of independent jobs and you don't want to overwhelm the computer as well, overwhelm the system. Yep. The next one is packet queue, which simply allows you to use PCAP files like an SQL database for looking at DNS traffic within those PCAPs. It's quite flexible. It's pretty fast. It processes about 100,000 rows a second, so it's pretty good. But the problem is every time you do a query against those PCAP files, you have to pay the cost of reparsing those PCAP files every time. So if you're doing repeat queries, it pays to put in some sort of database. And it's now maintained by OARC, so I'd like to thank Jerry for the work he's doing on that one. I know he's not here today, but we found a couple of bugs in it, so he was really fast in fixing those bugs. For the graphing front end, just Grafana. People know Grafana. It's pretty good. It plugs directly into ClickHouse, which is the database we'll be using, which Igor briefly spoke about this morning. Basically, I use this, write some SQL, and it charts that SQL. So, and it's looks fairly nice, and that's the main thing. Okay, so the main jewel in the crown that is this charting system is ClickHouse. It's a columnist store database. I saw a really interesting talk by Cloudflare about it. I had a conversation with Martin Levy about it, which basically consisted of him holding me by the shoulders and shaking me until I agreed to go and see the talk. It was super interesting, actually, the talk, it turned out. The big thing that I got out of it was they ran a competition to see who could guess how big their cluster was that they were using to stream 1 million events a second into. And it was actually 9 servers for processing 1 million queries a second, and that was with triple redundancy. So it's a pretty fast product. Yandex, which is the maker of ClickHouse, they're from Russia, and they have a cluster of about 400 servers, and they're real-time querying petabytes of data. So it's pretty impressive, at least to me anyway. Okay. Some of the bad features of ClickHouse, as an SQL database, it has no update or delete, which means once you put stuff in there, it kind of stays there, which when you're storing logging data is actually pretty good. It doesn't really matter. The documentation is translated so it can be a little bit brief. And on the primary storage data types, the first column must be an event date, which is easy to get around. You can just set it to 0 if you want, if you're not doing time-based data, but really it's used for storing time-stamped data. And when I say accumulated results, I mean when I say the working set, I mean the accumulated results must fit in RAM. So if you've got a server with about 96 gigs of RAM, your accumulated results must be less than that, which I don't think we'd be interested in reading. And they recommend batch inserting as well. So you can't they don't recommend injecting a single row at a time. You've got to do it like at least 10,000 at a time, up to once a second. Well, at minimum once a second. Or maximum? Whatever. Okay. Less often than once a second. Okay. What's great about it is extremely easy to set up. Basically install it, that's it. There's no knobs to twiddle. The performance is so brutally fast, they don't need any knobs to twiddle. The documentation, because it's so brutally fast, is succinct. So unlike Postgres, you've got pages and pages of performance documentation you have to read to make it actually work. With this, there is none. It just works. There's tons of analytics functions built into it. I think Jeff knows what a Pearson correlation is. You can just tell it Pearson correlation on 2 columns, and it'll give you a number. So the top one there is a correlation between the query flag and the answer flags on packets. You can see the correlation is 0.99, which is as close to 1 as you're going to get. And then there's the an example of where it doesn't correlate is query flags to answer code, and there's a negative correlation there, so it doesn't match at all. And I'm sure Jeff would love to explain that to anyone at a bar later on as to what that means. Clustering is extremely flexible. You basically can either manually shard it by just inserting into different hosts on your cluster independently, or you can get it to automatically shard that data through a single source. Mirroring is very easy. Just set up Zookeeper, point it at Zookeeper and say, make sure that these tables are the same on all of these hosts, and it just happens. Some might say that the edges it has are a little bit sharp, because if you do things wrong, they go drastically wrong. But I like to think of them as aerodynamic edges for speed. And the other thing it does really well is quantiles as well. It's super fast at that. And you can see that's like 330 million rows, and it took about 4 seconds to get quantiles for all of that. Okay. I'm going to compare Postgres and ClickHouse. I know this isn't a fair comparison because they're totally different databases used for different things. I haven't done much performance tuning on Postgres, but I did try to make them as similar as possible in terms of the table definitions and setup. But like I say, my point is not to compare the software packages, it's the concepts of a columnar versus row storage database. So in a row stored database, you're storing individual rows as packets on the disk. So when you want to look up an individual row, just go to that part of the disk, pull that row off the disk, you're done. With columnar store database, you actually break up those rows and store the columns independently. And then if you want to get a whole bunch of data out of one column, it's very, very fast. But if you want to get an individual row from those columns, you have to go to each of the columns, figure out the offsets, and pull it out. So it's much slower at that. But it's great if you just want a sequence of data. So if you've got sorted data, it's very, very fast. Also, because we're storing logging data or time-stamped data, there's some problems we don't have to worry about. One of those is race conditions. Because you're not updating the data ever, you can just write that data and not have to worry about locking or contention around those rows. Because the data is also stored in a columnar format and it's sorted, it's compresses extremely well, and I'll talk about why that's an advantage a bit later. And it means yeah. Okay, so here's a quick performance comparison. You see there, we're doing pretty much the same query on Postgres and ClickHouse. The Postgres query is taking 133 seconds. The ClickHouse one is taking about 4 seconds. What I've cut off there is the number of rows that have been queried. So in Postgres, it was 240 million rows, but in ClickHouse, it was actually 4 billion rows queried. So that's quite a performance difference. In fact, it's 2,300 times faster, assuming a linear scalability for both products. If I was to do the same query in Postgres on the same size database, it would be about 38 minutes. I did try some optimizations by adding indexes to those on Postgres, and it made absolutely no difference at all. So yeah, whatever. Here's a slightly more contrived example. This is with a slightly more optimized ClickHouse database. It had about 121 times as many rows, so we're up to 40 billion rows now. The Postgres query was 112 seconds, ClickHouse about 128 seconds. Again, it's so much faster. And again, this is almost no optimizations. A little bit, but not much at all. Even I could do it. But again, if we were to invert this and look up a specific row inside that database, Postgres would have totally kicked ClickHouse's butt. So it's a compromise about of what you're using that tool for. And another one of the big advantages of ClickHouse was compression. So it compresses all the data as it reads and writes it to disk. Here you've got the Postgres database taking up about 37 gigs for the primary table, not including the indexes I created in my attempts to optimize it. And you've got the ClickHouse data there, which is 17 times larger, but only takes up double the space. Sorry, it has 17 times more rows, but takes up double the space. And this is an advantage because it removes I/O as a bottleneck when you're reading that data from disk, which means you can buy cheaper disks or slower disks that are much larger, so you can store a lot more data. And they've got ZSTD as an experimental option as well. It uses LZ4 by default. Yeah, okay, so how do we get that data? We just dump it off the network using DNS cap and then rsync it from site to site until we get it to where ClickHouse is. We transform that data just using this method, using this chain. So it was just to PCAP, packet queue into CSV, CSV into temporary table into the final table. We're going from a temporary to a final table because we need to modify the data types so they're more efficiently stored on disks. So, changing IP addresses to unsigned 32-bit integers or 16-bit protocol identifiers into 16-bit data fields and stuff like that. And it actually saves quite a bit of space doing that as well. And that was one of the problems with Postgres is they don't implement unsigned integers, and their response to the question about that was like, well, it's not in the spec, so we didn't bother doing it. So, okay, whatever. I did add one little step to that, which made the performance much, much worse. I'm pre-matching queries and responses and storing those as a single row rather than storing the queries and responses separately. It's actually made the database 30% smaller, even though it halved the number of rows, just because the rows are twice as wide. And my Perl is extremely bad, so it's quite slow, and it's probably like 90% of the CPU time spent actually importing the data. So my initial exploration was 1 day's worth of data from one name server, and that came to about 60 million rows, and I didn't have any problems on my test infrastructure for that. I got 9 days worth of data, so about 500 million, and I started getting performance issues. It was fine for generating one graph in Grafana, but if you did 12 on a single page, it just freaked out and wasn't too happy about it, and it took too long. My platform was actually a Mac Mini 2012, running off a USB disk, so it was not the fastest thing in the world. What I did was I left the graphs up somewhere real public so that my boss could see them, and when I ran out of disk space and the graphs stopped working and the boss asked why that was, I immediately got his credit card to get new disks. So I managed to scrounge 3 servers. I bought 4 new 2 terabyte disks to store all the data on. I actually didn't need 2 of those servers, so they're still sitting spare, and only one of those boxes is currently used. And again, this is like 5-year-old hardware. And I scrounged a bunch of RAM out of the Hadoop cluster that Seb doesn't know about. And I also stole some SSD disks to act as L2 ARC for ZFS as well. So my coworkers probably know that now. So where are we now? This was back in December. This number was true. So the CSV files are actually quite a bit larger. Even gzip9 take up nearly 2 terabytes of space. And the ClickHouse database was sitting about 1.5 terabytes on there without any worries. I'm actually, I think it's up to 40 or 50 billion rows live of data in there, and I'm waiting on some hardware to actually productionize it, and then we'll probably start providing graphs publicly for some of this data. Now, you may have noticed that I've said nothing about what my topic is, which is data analytics. I'm not a data analytics guy, so Jeff, don't jump on me too hard when I talk about analytics. So I thought I'd come up with an example process, something that I thought would have been a good example for here. So I thought I'd figure out what our top 10 biggest users were by ASN. I've anonymized the results in that I haven't translated the ASN to names. So, so if you want to look those up, I guess you could, but it's anonymous, right? So this is the SQL. It's pretty simple. Just limit it to top 10, and here are the results. I was immediately distracted by the results. You can see there's 2 results in there that are weird. So there's one here, an AS, that gets 0 NX responses. It's never looked up a domain that didn't exist. I thought that was a bit weird. And then the one right underneath it, 99.5% of all the domains they look up don't exist. So I was immediately distracted and decided to look into that rather than work on my talk. And so I just added another couple of columns, which is the domains that looked up, how unique were they? So what percentage of the lookups weren't a repeat? And you can see the one with, was it 12714, was doing 30 queries a minute on average from about 300 hosts, evenly cut up, and there was no caching involved. So they would look everything up all the way from .nz all the way through up to the domain they were looking up. So they looked up dns.net.nz quite a lot. And it looks like they're doing some sort of validation as well, because they were doing DNS key lookups along with that as well, which I thought was pretty interesting. So I guess they're doing some sort of validation with that. I expect it's some sort of monitoring platform. I don't know who it is. I didn't bother looking it up, anonymous and stuff like that. And the next one down, which was the other really odd one, was ASN number 51747. They were doing their traffic from approximately 100 hosts, but they had a 0.5% of the lookups they did came back as a domain that existed. And the traffic was evenly spread over about 90 of the hosts that were in there, and they were getting that really, really bad lookup performance. But then there were a couple of hosts outside of that 90% that were getting 100% okay. And when I looked up the domains they were looking up, it was our name servers and the SRS registry. So I suspect who's behind that, who's using that AS is some sort of IP organization, who's looking up intellectual property organization, looking up copyrighted names, making sure that they're not registered, right? And I've done a bit more exploration than this, and I do know that there are intellectual property organizations because continually looking up domains and who owns them to make sure that their clients' rights aren't being breached in any way. So, and that was something I didn't know even happened. I thought there were people out there trying to brute force the zone, but I didn't realize why they were doing it. It becomes a bit more obvious when you can see the business names involved in that. Okay, some other stuff that turned out to be pretty interesting was looking up the flag combinations that were set up from all the traffic we're seeing. So the middle column there on the top set of results is the total amount of traffic we're seeing. So 32% of the traffic has DNSSEC enabled, and the CD bit set indicates that they're going to do checks themselves, and they don't want us to do any validation, which is good. And the 80% of their replies come back with no error. The next one down was a little bit more interesting. So 11% of the traffic we see comes through with the recursion desired bit, which means they think we're a recursive name server, and they're getting 6% no error. So like 94% NX domain over all traffic. So it's a pretty good indicator that people who set that up are probably trying to bulk harvest the zone itself, or it's a really badly written stub doing something I don't really understand what they're trying to do. And really, that's what this sort of project has taught me. There's a lot more questions and questions out there to try and answer, so I can't answer all of them for you right now. The next thing I did was, I thought that was pretty interesting, so I broke it down by the resource record type queries they were doing as well. And you can see the RD ones, they're looking up NS records as well, which makes it even more interesting. And the no error rate goes down even further. So they're clearly doing some sort of bulk harvesting using a client that sets the RD bit. Just a badly written Python client, I expect, because I think that's the defaults for the Python DNS client library. Another thing I did was queries with the 80-bit set. So you may not know the 80-bit, if that's set, the client's indicating they want you to send back authenticated data, which again is like they assume we're a recursive name server, and they want us to do DNSSEC validation on data. And I kind of broke that down, and you can see there's some interesting little spikes in there, like 21% uniqueness of names. So they're doing repeat lookups on the same name, but mostly the top few ASNs are doing extremely unique lookups. So they're some sort of running through big lists of zones. And again, really high NX domain totals in there. So this is kind of the rabbit hole you end up going down with this analytics stuff. It's fast enough that you can figure out what the SQL is, type it in, have a sip of your coffee, then come back and it's complete. And that's the kind of flexibility and power that this sort of software is providing us for almost no input from my end, other than data and not too much of my time. Another query I got was from my boss was like, hey, is there a correlation between clients that set the RD bit and doing MX lookups? Because he thought there could have been a correlation with badly written spam bots that have a client that doesn't set the flags properly on the packet, but then is doing MX lookups to try and find mail servers to send spam to. And we didn't really have enough data, but to make any sort of actual conclusions about it. And I think the conclusion was there is no correlation with that, but we didn't have enough mail data to reveal. But it was kind of one of those things that I could just quickly throw together in about 10 minutes, show him a graph of what that looked like, and he could query that back over the 2 months of data that I had. And another thing I added there, unasked, was when people did recursion lookups expecting recursion, what were the resource records that they were looking up? And it was mostly the purple. It was quite popular. I can't tell. I think it's... Sorry? Yeah, you're right. It is NS server lookups. Yep, that is the bulk majority of it. So MX barely even registers on that scale. Another thing I did was recursion desired by site to see if it was geographically or at least AS topographically related as to where we were seeing those recursion desired lookups from. And there is a little bit. You can see the yellow lines, which is Stockholm, seems to be super popular with recursion desired. And also the unique number of addresses we were seeing with the RD bit set. I thought that might correlate to bot cluster, whatever you call it, activating, then deactivating, activating, deactivating. Something that's actually useful for work was the configuration validation. So here you can see the latency of one of the sites. Again, the 95th percentile line, plus or minus 5% worst latency, and then a 50th percentile latency as well. What I did there was actually modified the CPU availability to bind. I just cut down the number of CPUs it could use and immediately saw that change in performance, where if you were just doing the queries using a monitoring script written in Python or something like that, you probably wouldn't see this latency variation. And I didn't have to do any active monitoring. I was just passively pulling it off the network and seeing the changes live as they came out. Another useful thing that popped up when I was doing this was the RFC 6888 came into force, which means that CAs have to look up CAA records, which basically indicates that a domain owner can indicate which CA is allowed to issue certs for their domain. That became mandatory for CAs to verify that before they issued certificates. And so you can see there's some testing, and then about on the 8th, it becomes production, and everybody's doing those queries, and you get those spikes consistently from then on. So I didn't know about the CAA thing, because I don't really follow the CA stuff. I'm more of a Dane TLS guy. TLSA, sorry. Yeah, I had to look that up, and it was a learning experience for me as well. Other useful things is it can show interesting inter-site variations. Again, becoming aware of issues or differences between sites and the data that we're providing, the responses we're providing back. For example, there you can see the difference between Christchurch and Sydney. For whatever reason, Sydney has a reasonably consistent average query name length, but then down in Christchurch, there seems to be some provider who's doing lookups of a specific type. I'm trying to see if I can see him here. No, it looks like he didn't make it back from last night. And then there's the average packet reply size as well, which is related to the type of lookups that is happening between those two sites. I don't know if you guys keep track of all of the latest that's happening in the DNS world, but PowerDNS did an interesting blog about a thing called logarithmic percentile histograms. And I thought you're just going to have to look it up. I'm not going to explain it. But I thought I'd give it a go. And it's basically showing worst performance within a logarithmic percentile on a graph. Obviously, that's not a graph. That's just a table of numbers. So I made it a graph. And this is directly in SQL. It just has that sort of functionality, which is super cool. You should probably look up the blog if you really want to understand that. And if you have read that, then that's pretty cool. And it was only like a page of SQL to do that. And also, because it was easy, I was I wonder if there's a big difference between the different types of resource lookups that people are doing, or based on the responses we're sending back, if there was a difference in the latencies there. So that's another thing that I could really break down as well. How much time do I have? Oh, I'm over time. Sorry, guys. Anyway, so what's the summary of what I'm talking about? These are extremely simple and powerful tools. This is the installation process. It's literally a page with comments of Bash, right? So you could do this, just set up a Ubuntu box, install. You can have the slides later. You don't need to take a photo. It's cool. But yeah, you just install it and start stuffing data in it. I had to do some whois stats. Literally took me like half a day just to dump all a week's worth of whois data. Most of that was just waiting to parse CSV, dumb CSV logs. So yeah, so any questions about that? That's the end of my talk, by the way. Really simple, powerful devices. Go out and do it. No question? Oh, no questions? Oh, we've got Igor's got a question. Igor's got a question. Sorry, is it Igor or Igor?
Yes, yeah. No, you're right. The first one.
Okay, yeah.
There's two different Russian names. My one's pretty random. What did you think? Like, can you probably say what is can be used for in terms of like what kind of data? So, like, for example, do you think it's can you use it for do some analysis on the IPFix flows or something like that? So, So
Yeah, that's a good question. Sorry, that should have been the start of my talk, which is that this is an example of how I used it. I've got a bunch of other things I'm going to use it for, but really anything you can stuff in here that's time-sensitive or time-stamped data, this is absolutely useful for. Even if it's not time-stamped data, it's still pretty useful just because the speed at which you can process that data. It makes the data exploration super quick, and it's fast enough you can graph off it. Like, come on, it's nice. One guy over behind you there, Igor.
oh yeah.
So you said that you can't delete anything from the database. How do you handle the
Yeah.
growth over time?
So the talk was longer, and I did explain how you do that later on. But what it does is it partitions the data up by month. So you can actually just drop partitions off the end of it, so you can get rid of older data like that. They are at some point planning to add the delete and update functionality one day. It was on the roadmap for this quarter, but it hasn't happened yet. They've other really cool stuff like adding the they added 2 cool new features. Actually, one is Kafka. So you can take a Kafka topic and make that a table and then apply queries to that and update other tables based on that data, which is pretty cool. And the other one was, they implemented a neural network modeling system in it. So you can load up taught neural networks into it and apply that to data as it comes in live into the tables, which is also pretty cool as well. Using, they call it Cat Boost. They have some really weird product names. The other one is Cocaine. So ClickHouse was the most normal sounding one, but yeah. So any other questions around that? Cool, great, thanks.
Right, cool. I've got some slides. Yes, so my name is Shane, and when I'm not busy solving all of your lawful intercept problems, I like to dabble in a little bit of research. And my particular favourite topic is application protocols and traffic classification. So what I'm going to be talking about today is some of the things I've learned over my many years of studying this stuff. And really it's going to be a bit of a history lesson. And then leading up into what application protocol designers are thinking in this day and age. So where I'm really coming from is that I have a firm belief that both as an academic community and as an operational community, we have a very poor understanding of what the full range of application protocols are that are out there that are using our networks. Up until now, particularly in the research field, the focus has just been on the easy targets. Your sort of heavy hitters, high volume type things. So we know a little bit about HTTP, we know a little bit about BitTorrent, we know these things exist. But once you get past, say, maybe those top 10 or so protocols, could you really name the other ones that are going on your network at any point in time? Probably not. So really we don't have much of an idea as to how application protocols have evolved over time, or even what a contemporary traffic mix looks like today. But when I say that we don't have a good understanding, I actually mean all of you, because I've been looking into this sort of stuff for many years now. I've spoken about the Libprotoident project at previous NZNOGs many times. But basically what it is it's open source, lightweight packet inspection library for doing traffic classification. We've been working on it at WAN for many years now. As of the last stable release, which was, I think, late last year, we have support for 435 unique application protocols. So when I say lightweight packet inspection, what I'm talking about is a very, well, in contrast to, say, deep packet inspection, we're only looking at maybe the first 4 bytes of payload observed in each direction for a particular network flow. We're only looking at the size of those first payload-bearing packets in those directions, and the TCP or UDP port numbers. So we don't go any deeper into the packet payload than that. We don't look at IP addresses, so we can work with completely anonymized traffic as well. So what I've done is I've taken all 435 of those protocols, put them in a spreadsheet, and started annotating them with a bit of metadata about each of them. So things like the category or the purpose of the protocol. So is it a peer-to-peer protocol? Is it a gaming protocol? Is it a chat protocol? country of origin for the application or the person who is credited with inventing the protocol, when that protocol first appeared on the internet, whether that protocol is publicly specified, like through an RFC, or whether it's proprietary, and if there's any information about default ports that that application might be using. What I've also done is I've taken a good look at the Libprotoident rules for each protocol itself and tried to sort of provide a bit of a taxonomy based on how those rules are structured and how that gives us some insight into what the protocol actually looks like. So do we actually need to use the port number? Like, does the rule use the port number to create a successful match? Does the rule rely on the packet size, or does it just use the payload information? With the payload itself, does it look like textual ASCII characters, or is it more, just seemingly random looking binary? Does the payload have some sort of wildcard type bytes in it, or are those 4 bytes always relatively fixed? They stay the same, they're the same 4 bytes. And can we match the protocol just using one direction of traffic, or do we need both a request and a reply to be able to make a successful match? And what I'm hoping to have achieved through all of this is I can reveal a bit more about the history and the story of the internet from this sort of unique perspective of the application protocols as they appeared on the internet. And in particular, I'm interested in trying to identify and report on any trends or adjustments that have occurred in the protocol design mindset. And in particular, things like people's reactions to things that operators and people do to try and sort of engineer or shape or block certain types of traffic. And the last thing I would like to do is to try and make my life easier by having a bit more of an idea of how modern application protocols work, to make them a bit easier for me to identify. And there's also always this sort of lingering question, is DPI or LPI or any form of packet payload inspection still going to be viable? I mean, people have been talking for a long time about how, well, everyone's just going to encrypt everything, so what's the point of even trying to do this payload inspection? Does it still work in this modern day and age? So this first graph that I've thrown up here is, it shows the number of new application protocols over time. Dating all the way back to 1981 through to 2017. So this is a year-on-year number of new protocols. There's 2 bars per year. I've split it by TCP and UDP. So the light-coloured bar is TCP, the darker one is UDP. So I'm just going to highlight a few particular points in this graph. So this sort of area with very little activity, this is what I call the pre-commercial era. So this was back when the internet was for serious business only. You weren't allowed to use it to make money. You weren't allowed to use it to do, fun things and entertain yourself. It was basically an R&E network, and it was primarily funded by the US government. So protocols were developed slowly over time by a small group of academics, and they tended to dribble out as they sort themselves out or came up with ideas. Now, bear in mind that some of these numbers for this period are going to be very underreported, just purely by virtue of the fact that there would have been protocols invented in this time that had completely died out by the time that I started developing Libprotoident, so there's no point in me trying to write rules for protocols that don't exist. After 1995, we start to see a very strong upsurge. A couple of notable points is online gaming begins in 1996 with Quake. The instant messenger wars with MSN Messenger, AOL, Yahoo, that contributed to a lot of that spike in 1999. The dot-com bubble burst here, so we get a little bit of a lull. This is the period that I've called the peak innovation period. So this is sort of characterized a bit more. You'll notice that the UDP lines are a lot bigger than the TCP lines during this period. So this is when people are starting to use the internet for real-time applications, and they figured UDP is a much better idea. So this is when your Skypes and your various streaming platforms are just starting to appear. And now we've sort of reached something that's a bit of a steady state, if not a small decline, in terms of the number of new protocols that we're seeing. So this graph here shows a cumulative volumes for protocols for the 4 most popular categories in my data set. So there's about 30 different categories, and I obviously can't show all of them on the same graph, but these are the 4 biggest ones. So you will have noticed from that gaming is absolutely massive, so it just keeps growing year on year. In fact, over a quarter of the protocols in my data set are for games. And this is really because the gaming industry is a bit funky. They are very, very concerned about people reverse engineering their protocols, because then they can use them to cheat in online games. So every time you release a new game, you effectively start again from scratch, right? So that if anybody had started reverse engineering your previous game, all of that work is wasted by the time that the new one comes out. The other problem that they're concerned about is people running underground servers. So rather than using the official game company run servers, that people start up their own ones where they run them for free or let you do all sorts of wacky, cheaty things on them. So you get this whole thing where in the gaming industry there is nearly no protocol reuse whatsoever, right? They will completely wipe the slate, even if they're reusing just about every other part of the game for their sequel. They will start again network-wise. So we get this steady year-on-year growth. For the other categories, it's a little bit different. So with peer-to-peer, we saw that there was sort of this golden age between 1999 and about 2003, when you had all these competing peer-to-peer platforms. You had your Kazaa, and you had your LimeWire, and you had your Nutella and Emule and things like that. But you can kind of see that after about 2005-ish, that basically innovation in the peer-to-peer scene stopped, right? We got BitTorrent. BitTorrent worked. Nobody's figured out how to really stop it from the content provider perspective. And so it just works, and there's no need for anything else. The chat scene is basically defined by these 2 little periods. The desktop instant messaging, which I mentioned earlier, and then you'll notice that from about 2008 to 2012, we've got another little surge when mobile instant messaging became a thing. So I'm talking things like WhatsApp, WeChat, Kik, all of those little messaging apps that you get on your phone. But by about 2012, the entire market had kind of been consumed, and there was not really any space for anyone else to move in anymore. The tunneling one, I just want to point out this little surge that we're getting right now. This is almost entirely due to mobile VPN applications. So people downloading little VPN apps from, well, some of them are a bit more P than other, shall we say, when you download them from the Google Play Store. Country of origin, so unsurprisingly, the US is by far the biggest producer of protocols, particularly in that early era, but they've sort of maintained their lead. But actually, the US aspect of this is very interesting in that almost all of the protocol development coming out of the US in the last 3 or 4 years is games, nothing else. It's just purely the fact that the gaming companies are all based in the US, and so I attribute the protocols to them. Any other type of application that's coming out of the US is more than likely just building on top of HTTPS, which just counts as one protocol that was invented, back in the late 90s or whenever that came about. The other very interesting line there is that red one down the bottom, where you can see that China appeared in 2003 and is now definitely moving up and is a clear second place, and then the rest of the world just kind of dribbles on behind. So China is, I want to be careful here how I phrase these things. China is an interesting place, an interesting market from an application perspective. So a lot of that early growth started with peer-to-peer content sharing, both in terms of your traditional style file sharing through the Xunlei platform, and then as well as the peer-to-peer TV live streaming over the PP Live and PP Stream platforms. But China is both a very large market, but is also a very isolated market, both in terms of linguistically. Right? It's not easy for them to necessarily be able to adapt to Western apps in terms of the language, but also in terms of sort of a commercial isolation, right? It's been very difficult for Western companies to be able to get any sort of market share there on the ground. So what actually happens is you get a lot of Chinese companies that invent alternatives, if not clones, of the existing Western applications. So you get this duplication. The other thing from a protocol design perspective is I've noticed that there's a lot of things that you can attribute to being the result of the Great Firewall and how that kind of affects the mindset of the protocol designers. So you get things like they don't use HTTPS. They write their own custom encryption protocol because they feel a bit more that they've got a lot better chance of, the government doesn't already have the keys to that one. You see that there's so many different possible VPN applications that are trying to compete for market share. And the other thing, if you remember my talk from last year, they love to steal ports that you would normally associate with other applications. So moving on, the next graph I'm going to show is a little bit about specifications. So protocols, in terms of specifications, generally fall into one of three categories. The two big ones are they're either publicly specified, so if somebody either wrote an RFC or there's a public document from the person who wrote the protocol. And this means that if you want to implement that protocol, there's something there for you to work with, and you can write some interoperable software. From a traffic classification perspective, it makes my life a lot easier because if I see something like a clear phrase, I can Google that and I end up eventually finding the specification. I go, okay, well, that's what that is. Proprietary protocols are the exact opposite. The protocol is treated as a trade secret. There is no documentation, there is no public information, and it's a bit harder for me to identify. Then there's sort of this weird grey area where somebody has eventually reverse engineered a protocol and they've put up their source code on GitHub or something like that, and I can kind of use that to make my life easier, but it's really not that official. So if we look at the specification status of protocols over the years, you'll see that in the pre-commercial phase, everything was pretty much public. It was just a bunch of academics writing RFCs, things like that. In the early post-commercial phase, we still had quite a lot of publicly specified protocols. So this, again, academics and industry groups working together to come up with standardized protocols for new applications. But from about 2003 onwards, it's all proprietary stuff. So another thing I looked at is whether the payload content was nice ASCII text or gobbledygook binary. So obviously when you're designing protocol, it's a lot easier for you if you use text because you can debug it on the wire, it's human readable, and it makes your life easier, but it also makes people like my lives easier and the people who are trying to block your traffic's life easier because they can easily look for those phrases and block you as well. When you use binary, it's a lot harder for a human to inspect, and you also gain quite a bit of space efficiency as well. So again, looking at things over time, we see that, while binary has generally always been a little bit more popular than text, there's been a very significant divergence, again, around that year, 2002, 2003, to the point where the binary protocols far outnumber the text ones. So there's obviously a few reasons for this divergence. So a lot more real-time applications from about 2003 onwards. So, those require a lot more protocol efficiency. They can't afford to waste bytes on, spelling out everything in ASCII text. The threat of DPI discourages people from putting any textual content in their protocols if they want to avoid being detected. And going back to a couple of things that we've already seen, the dominance of game protocols, in which case, again, protocol efficiency is important, and also the growth of Chinese applications, because ASCII text is not really that helpful necessarily if you don't speak a language that's built on that particular character set. So another thing I touched on, so whether the 4 bytes of payload that is used by Libprotoident to make its match, I've looked at whether that 4 bytes is static, so it's a fixed 4-byte pattern that's easy for me to recognize and spot. For example, it might be a textual one like the HTTP GET, but it could also just as easily be a 4-byte fixed binary pattern versus the variable ones where there might be some sort of wildcard. And so therefore, if that byte can vary, then it's much more difficult for me to recognize the fact that this is a pattern that appears a lot, because it actually might be 200 variations of that pattern that all appear sometimes. So if we look at it over time, this graph is a little more interesting. You'll see that there's a, oops, again, oops, my battery died. So you'll see that actually we still have quite a lot of, even though fixed payload type protocols are relatively easy to identify, you'll see that they're actually still more common than the ones with wildcards and other bits of obfuscation in them, to the point where actually the gap is widening. And this is because even though it would be nice for applications to be able to it's nice for the applications if they're trying to remain undetected to be able to randomize the initial bytes somewhat. The application themselves still need some way of recognizing that the traffic that they're receiving is actually destined for their application and not just some random internet backscatter. So there's a lot of protocols are still generally designed at the application layer to have some sort of clear either handshake-based structure or some sort of magic number at the start of the protocol exchange so that they can be much more easily identified. How am I doing for time? No, not too bad. So port numbers. So we all know how port numbers work. If you are a server, then you sit there and you listen on a specific port number. The client magically knows which port number to talk to you on. And so, traditionally when you're developing these things, you pick a default number and you both start with that and hope that you can make a connection. If your protocol ended up being particularly popular, then that port number got standardized by the IANA, and everyone knew that that was the port number that you ran on. So things like 53 for DNS and 123 for NTP and so on and so forth. But then peer-to-peer came along and supposedly changed everything. So initially peer-to-peer apps did the same thing. They had a default port number, but BitTorrent was 6667 and things like that. But then everyone decided that they wanted to block it or shape it or detect it or do something about it. And so BitTorrent developers started going in and adding these out-of-band channels to allow peers to communicate the port that they are listening on without, without having to predefine it in the software. So these out-of-bound channels started to appear. And then at that point, people decide, well, port-based classification is useless because all our traffic is BitTorrent anyway. Here's an expensive DPI solution. But actually what has happened is that the number of protocols with known port numbers has continued to grow over time. So if we consider unknown as sort of the protocols that use dynamic port numbers, we can see that there's actually quite a large gap between the two. So in other words, port numbers are still default port numbers are still being used and are associated with these protocols. And the reason for this is pretty simple. It's that going to all that effort to develop either some sort of out-of-band channel, and you'll also need some form of NAT traversal to reach most people. That's a lot of work for not necessarily a lot of gain, right? Most of these protocols don't have any concerns about being detected. But taking that a little step further, if we have a port number associated with a protocol, do we necessarily need to use that port number to achieve a successful match? And so what this tells us is that we can get insight into both the distinctiveness of the protocol as well as whether that protocol relies strongly on that port or not, right? Because if a protocol has an associated port number, let's say 1000, but 90% of that traffic for that protocol actually isn't on port 1000, then there's no point in including an insistence on the port number being 1000 as part of your matching rule. You've missed 90% of the traffic. So what we see in this graph here is that in the early days, well, for the rules that match protocols that were developed in the early days, should I say, many of them actually require a port number to achieve a successful match. And the reason for this is twofold. One is that everyone had a port that they generally used 100% of the time and was well known. But also, many of these protocols back then used what I would term common protocol structures, which meant that we actually needed to use the port number to disambiguate between them. For example, if you think about SMTP and FTP, both of them use the exact same reply codes in their initial exchanges, right? Both of them generally start with something like a 220, right? And so if I see 4 bytes to a 220 space, I've got no idea which one it is unless I look at the port number to try and disambiguate. But moving on from that, we then started developing, well, we started seeing protocols where we could write rules that didn't require the port number. And this was because even though maybe the port numbers were becoming more dynamic, in addition to that, the payload patterns were sufficiently distinctive between different protocols that we didn't need that extra port information anyway. But now we come back to the modern day, and protocol patterns are starting to get a bit more ambiguous, and we need to use port numbers a bit more often to resolve any ambiguities. So unidirectional versus bidirectional. Unidirectional rules are great in that they let you work with asymmetric traffic, in that they let you reach a correct classification sooner. So if you're trying to do it in real time, you only need to see one direction before you don't have to wait for the other end to reply, even if it does reply. But of course, for it to work in one direction, you've got to have a very distinctive payload pattern. And we can see that over time, really unidirectional has basically disappeared. So the patterns started out being generally pretty distinctive, and so you could match just with the one direction. But modern era protocols, no, not so much. Patterns are very ambiguous, and you need to see both ends of the connection to be able to make a successful match. So the last one I've got here, packet size. So quite often we use the packet size alongside the payload to make our classification decisions. This is generally useful in the cases where the protocol either has some sort of static packet structure, and so therefore the first packets are always going to be very much the same size. Or if those packets vary in size, there's a good chance that that protocol will include a length field in those first 4 bytes, and so I can match the two together to insist that is the case. If packet size is not required, then that probably means that either the payload pattern is so unique that we don't need the packet size for any disambiguation, or the packet size is variable and we don't have a length field to figure that out. So as you can see, packet size definitely is much, much more required from, again, about 2003 onwards. So yeah, almost all modern protocols, we need not only the payload, but the packet size as well to perform the match. So what have I learned from all of this? So from a historic perspective, we can definitely divide the history of application protocols into a clear set of eras. So we have sort of that early pre-commercial era, the initial post-commercial era, or the age of innocence, as I sometimes call it. That little lull around the dot-com boom, the Renaissance when we kicked it all off again with a lot of real-time stuff, and then we have this more modern era from about 2011 till now. The thing I would say most about modern era protocols is that they're essentially treated by their developers as disposable, right? There's a rapid design, it's a minimal feature set, and as soon as it comes time to do something a bit different or to try and extend it, it usually ends up being a lot easier to just throw it away and start again than try to extend the original protocol. So there's not a lot of what you would say is design processes or thought going into how these protocols are produced. Modern payload patterns are a lot more vague than they used to be. So I see a lot of patterns that look like 00000001 and maybe a 0000002 coming back the other way or something like that. And a lot of them all look quite similar or within that range. It's not like you look at it and go, oh, that's, there's like some letters in there or something that's actually quite useful and stands out. So we need a bit of that extra info. We need the packet sizes or we need the port numbers to make the classifications work. We've seen that generally these days protocols are proprietary, they're binary rather than text-based, and all of these things mean that I've got to put in a lot more extra effort than I used to identify and classify new protocols. The main sources of new protocols these days, gaming, mobile apps, probably no surprises there. China's a big producer now, so I spend a lot of my time downloading, installing, and playing random Chinese video games and Chinese VPNs. So I've learned a lot about UI design in China as well. The Western world, we tend to just build on top of HTTPS now. It's so ubiquitous. Every major application that's taken root in the West in, say, the last 10 years has probably been built on top of HTTPS. So aside from that gaming aspect, we do see very few new protocols coming out of the West. So having thought about all that, what is the future of DPI? Personally, I think there's still a bit of room to maneuver. So I'm still adding new protocols to Libprotoident, when I have time, which is very little now because I've committed to solving your other problems. But, I'm still seeing new patterns on a regular basis. I have a script that basically emails me the biggest contributing patterns every day, and I look at them and say, that's not one I've seen before, let's go have a look at it. So they do appear regularly, they do decent volumes, so we're not talking just stuff that turns up and does a couple hundred kilobytes of data and then disappears. This is stuff that's doing hundreds of megabytes a day at our organization anyway. But like I say, some of the patterns are still recognizable. So when I look at that email, I see something and I remember that I have not seen that before. That is new. That doesn't look like anything I've seen before. But it is a lot harder to go back and find the source because there's no documentation for these things. People don't even bother to really try and reverse engineer things anymore because it's not worth the effort. And so really a lot of it is me trying to find context in which that particular flow appeared, what was that person doing in the minute or two leading up to that, and maybe there were some plain text HTTP requests that start to point me in the right direction. So so I'm quite happy to take some questions now or later. If you're interested in Libprotoident and haven't looked at it before, we've got a GitHub, you can see that there. Otherwise, you can email me. The raw data I use to produce those graphs, that's all in a Google Docs spreadsheet that if you want to have a look at it, feel free. And do your own analysis of your own things. Cool. Thank you.
Cheers. Just out of interest, is cryptocurrency a sector that you've seen a lot of application growth in, or protocol growth in?
Yes, I do. If you actually go through the spreadsheet, there's at least half a dozen different cryptocurrencies that I've seen that I've managed to write rules for because they all quite nicely include a magic number at the start of their protocol. So they're not too hard to identify because somebody's usually documented that somewhere.
Cool.
So that, well, I'm afraid, there's quite a few. So I'm sure many of you are familiar with some of the joke cryptocurrencies that have made the news, like ones based on dogs and other memes that have appeared on the internet. I have rules for those. Those appear enough in the traffic that I monitor that it was worth me sitting down and writing a rule for dog coin and other things like that. So.
Hi, Hendrik from Marnet. Many of us will be storing either IP fixed records or NetFlow records, which tend to be based on that kind of source and destination IP and port number and protocol. Mm-hmm. Do you see any discussion of that becoming less useful and vendors just saying, let's just do source destination IPs for that sort of caching, or
so in
the reverse perhaps, getting more inspection inside the router for routing decisions?
Yeah, so it's interesting because the DPI industry itself tends to rely quite a lot on source IP and dest IP to make its protocol classification decisions, and that's a big point of difference between us and everyone else. So they'll go a bit deeper than, say, application protocol. They'll try and tell you more specifically the application. So they would, where we might say HTTP, they might say Facebook, for instance, because they know that this is an IP range associated with Facebook, and so they'll add that extra information. But really, if you're not doing stuff like that, then really you have to go a little bit deeper into the protocol stack and look at that payload. We try to touch as little payload as possible. That seems to work for us. But most of the other DPI products try to look a bit deeper because they're really interested in subclassifying that HTTP.
Thanks.
Donald? If you can get the mic to him.
Where is he?
Nobody likes the man from Spark. Is there a cultural bias arising out of the particular traffic that you're analysing? If you were doing this in North Africa, would you get different results?
I think there's definitely some element of that. Certainly I would say that we see a lot of these Chinese applications because we are quite fortunate to be a university and we have a lot of international students who pass through our doors. At the same time, I feel like the university network is actually one of the best places to be in terms of the variety of what you can see, because we have not only the research aspect, we have the university's commercial operations, we have the students themselves connecting both through mobile and whatever they do on any wired connections, and we also have data from the halls of residence where students live. So we sort of get this quite wide range of applications and activities that you wouldn't necessarily get in any other single one place. And that lets us get a very wide range. Whether that range is still biased towards certain demographics, probably. If anyone who wants to provide me with a feed from, say, North Africa or anywhere else that I can use as an extra source of data, I'm more than happy to do that. Cool.
Next up, we've got Tim. Oh, is this your dongle? Yes. It is? Okay, I was going to say.
It's not mine.
It's not yours. This is someone's dongle. Don't forget it.
It's a good one.
All right, I've got a lot to get through, so sit up, listen. I know it's 2:30, but hopefully you can learn something from this. So first up, I'm Tim from IX Australia. I'm a peering engineer. What I'll be giving you today, first up, is an IX update for New Zealand IX, and then I'll talk to you about our metric stack. So New Zealand IX was an association spun out of IX Australia following a successful trial in 2016 of the Auckland IX. The goal of the association is to support the internet in New Zealand and basically bring the peering model that we had and supplement the internet community here and the peering community that was here with another fabric. And what we found is there's been a great uptake, and I've got some graphs and bits and pieces just to show you what's happened over the last 12 months. So with regard to active peers, so after the launch in 2016, we gained quite a few peers, quite a significant jump, and then we've just had a few more providers pop up and join the fabric in the 3 locations where we are in Auckland at the moment. So there's been a slight addition of peers. However, prefixes has had a fairly linear increase for V4 and V6. So there's been a couple of very large providers we've added to the fabric that have really increased that prefix count. And then lastly, traffic increase has been exponential. So quite a few large peers, quite a few large eyeball networks, plus content providers are starting to pop Auckland as well and create a big presence there, which is definitely causing the fabric to grow and in the value that it brings. So if anyone has any particular questions about where we are, what we do, and what we can do to help the community in New Zealand, come and have a chat to us. Joe was here, but unfortunately he's had to get home to see to his family, but come and have a chat with me and we can figure out how we can help your community. So, with my remaining time, I want to run you through metrics and monitoring for IXPs. Before I started out this project about 12 months ago, this was the metrics that most people were familiar with. We ran cacti with the spine polar to collect 5-minute averages, which is not amazing because with RRDs they roll up. They average further, you get less resolution in your information. Cacti's not bad for giving you insight that you want to know up front, so the aggregate, so sum me all the ports and tell me what the total is. But if you want to dig in and say, show me all of this type of traffic or that type of traffic, you then have to go and create a new RRD and have it and create it from that point forward. It's much harder to go back and create a script to run it, pull the data forward, create the graph. It's a bit more mucking around. And it was manually configured. So we'd go in and you'd add the index for the port and then the next peer's port would come up and you were all good. Similarly, we had installations around Australia. So for each of the fabrics that we ran, so that's Perth, Brisbane, Sydney, Melbourne, and Adelaide, we had a monitor box with the polar installed and it would produce graphs locally. It's not bad. We got the insight per peer. We got an aggregate for each fabric. It was good, but we felt we could do better. So we came up with a list of requirements. What we wanted is the highest possible data resolution. We wanted to be able to see the difference that 1 minute versus 5-minute averages would make. And so looking back, this is some data for peer A. Yellow line is a 5-minute average, whereas the green line is a 1-minute average. So average is in polled every 1 minute. You figure out what the data rate is on a per second by the time that's passed between polls. You can see that the maximum on a 5-minute average was only 2.8 gig, whereas the maximum on a 1-minute average was 4.5. That's much greater utilisation. So if you start seeing a 75 or an 80% utilisation of a port on a 5-minute average, the likelihood that you are actually topping it out with microbursts and minute, 2-minute bursts that you're not seeing on your 5-minute average affects the performance of your link. We wanted to make sure that we got greater insight, but we wanted to make sure that the monitoring was resilient to network outages. How can we make sure we get greater data granularity with ad hoc analysis, but in the event that we do have a transit network failure or something does go awry, we're going to keep that data so that we have insight to look back and say, okay, there was a broadcast storm here or this link went down. We want to be able to see that. Future extension, because data processing and big data analysis is becoming a really popular area of interest commercially and in academia, we wanted to make sure whatever solution or stack we put in, we could extend later, add new insights and bring greater value to our members. Zero touch for new peers. I want to be able to turn up a peer's port and not have to think about monitoring. I do enough dealing with the peer, making sure that we're providing a good quality service. I just want everything else to work. And fully puppetised, we're already a Puppet environment, so this had to be set up with very little touch from an engineer. So in metrics collection, there's 3 parts to the stack. There's your data store, your collector, and your visualizer. So I'm going to run you through each of these 3 parts and how we chose them, why we chose the software we did, and how we made that work for us. So let's start with the data store. We went with Influx. Who here has used Influx before? Who's deployed it in production? Okay, smattering of hands. So it's an open source product backed by a commercial entity. So the commercial option gives you greater HA and commercial support, similar to the Red Hat model. It's a columnar database with an index over the time and your tags. So when I say it's tag dimensional, you can add metadata to your data points, and then you can use that to search on and query later. It's Golang based, so it's pretty fast, pretty efficient. All HTTP JSON API for interacting with it. They originally had this binary protocol, but they've since dropped that and gone for the JSON for HTTP method, I guess. And it's part of a stack of other tools that Influx Data, the commercial entity, has. Looked at Graphite. It's not dimensional, so your metric names are hierarchical. So you might have interfaces dot device name dot interface name dot IF octets, for example. It's not as easy to sum across metrics and do some more complicated queries with a non-tag based index. There's also a higher storage requirement. It doesn't scale nearly as well, so 12 bytes versus 2 per data point. Prometheus was very promising at the time, but it didn't have the long-term storage option. We wanted to be able to keep metrics for almost as long as possible. It has come a long way in the year since, so I definitely recommend people check that out. OpenTSDB, it's Hadoop underneath, and that has its own operational overheads. And Elasticsearch, again, operational overheads, and it's not, you can do the time indexes and you can get fairly performant queries, but I just felt Influx was a better fit, just due to some of the other tools available and that sort of thing. So Influx points look like this, basically. This is what metrics look like. Each line is a metric entry. You have a timestamp, so that's on the far right. The measurement name, which is on the far left. You have your set of tags. So your set of tags defines a query, a series, sorry. A unique set of tags is a series. So in my case, I chose the device name, the IF name, so that's the usually GE000, or our vendor chooses this colon syntax, and then the description. So if you change the description on the device, you get a new series. Not the worst thing in the world. And then you have your fields. So that's second from the right. In this case, it's IF octets. So I can query based on the tags, and then I can perform aggregations and operations on the data in the fields. So you can query it just like you would an SQL database. It's a very SQL-like syntax. In this case, I just want to show the series that I have. So show me the unique tag sets. So in this case, I want to look for descriptions that have 10084, which is our transit AS, and are from Queensland IX. So here I have a couple of interfaces from that. You can then do more complicated queries. So in this case, I do actually want to know some data. So the series querying just tells me what tag sets I have. This is actually asking, can I have the data, please? So I want to know in.bits.rate. It's just a metric name. So show me the rate of bits on the inbound direction from the measurement name, where, and I can then filter by tags. So IX and IF alias are tags, and then I check by the time dimension. And I can group by device and alias, IF name. So show me, split it out, show me each rate by each device over time. So this is fairly natural for anyone who's used regular RDB relational databases before, so it's fairly straightforward to just pick up and use. So we went with Grafana as the visualizer. Open source, it's quite pretty. I mean, I can't really argue. Some people produce some absolutely brilliant looking dashboards, very insightful. The tooltips are great. It's Golang on the back end, JavaScript on the front end, very responsive, very fast. It just seemed like a no-brainer. Dashboards are all JSON, all API based, so anything you can do in the web GUI you can do through the JSON. You're not limited with your data sources. Everything from Influx to MySQL to Elasticsearch, you can push through Grafana and pull out pretty information and mix and match them on the one dashboard. So that's something that we did actually end up using. And the templated and scripted dashboards are some of the most powerful I've seen. The tags are what make up your templates. So give me one dashboard, but create me a template for the interface number. So then I can just select my interface number or a set of interface numbers and build this dynamic dashboard. I haven't looked into using the JavaScript scripted dashboards, so you produce JSON from JavaScript that you load into Grafana, and you can do some very powerful things. It's on my to-do list. So we ended up producing a public-facing Grafana dashboard for IX Australia, and you can go through different dashboards and produce things that look like this, that give you a very quick heads up of what's going on, what is the current state, what has it been in the past, the kind of things that are really useful as an engineer looking, how's my network? So the collector. This is the bit that took the longest to decide and figure out, because up till now, no one's really done this well. Until I came across this open source project called SNMP Collector. It's open source, Golang backend, JavaScript frontend. You're seeing a pattern here for modern software, yeah. It's fast and flexible. So it'll only work with InfluxDB, but the power that it gives me on the front for collecting metrics is brilliant. What it will go through and do is you point it at a device, you tell it the metrics you want, how you want to collect them. Do you want to filter on indexes? So it'll run through every n periods, do an SNMP walk through my device, compare. So in my case, I use interface numbers because they're unlikely to change. You go through, you find the interface number, and you can put in conditional logic like, is this port up? Is this port 10 gig? Is this port 100 gig? And you can choose how it builds that index. So in my case, I only look for ports that look like a physical port, so no management or VLAN ports or LSP interfaces or management interfaces, and I want to make sure that the IF opera status is up. So I only want physical up ports. They're the only ones I want to collect metrics for. Then it'll go through and start collecting metrics. Really fast, properly threaded. Go handles concurrency really, really well, and it's really high performant. Best thing though is that it's 100% RESTfully controlled. So there's a GUI and there's a RESTful interface that the GUI uses. I looked at a few other things. Telegraph is where I started. This is the collector that Influx Data has. It polls devices one, then the next, then the next, and the next. So when you've got 48 10 gig ports, then another 48 10 gig ports, and another 48 10 gig, it would take more than a minute to do all of our devices. Even then, you'd have to run multiple instances, and it just got too hard. Prometheus SNMP exporter, same kind of deal. You can pass any indexes you want. It just didn't have the same sort of beautiful conditional logic that SNMP Collector provided. Collector is not bad, but the export through to Influx mean you get graphite-looking measurement names, and you sort of lose the flexibility of the Influx tags. So, although Collector is really, really fast. So this is what the collector looks like. Fairly simple JavaScript GUI. You've got all your object structures down the left-hand side. You put in SNMP OIDs, you build them together to create measurements. You can then bulk put measurements together into a measurement group. So say I've got a peering switch. I want to know interface status. I want to know the fans, the environmentals. You group them together, and then you can apply that to a device. And these are the kind of OID conditions. So in my case, I've got extreme up physical ports. So it'll only look for ports that look like they're physical and that they're in the up status. Had a dig behind the JavaScript UI, and it's just all RESTful calls, pretty predictable. That meant that we could automate the population of these. Add a new device. I just want to add a line into a file, commit it, and let Puppet take over. So that's what we did. I built a custom Puppet module that is able to talk REST to the collectors. So we've got one collector in every state. And I've got these data structures within the Puppet module to be able to populate the collectors. So we have maybe 50 or 60 or 70 different OIDs I want to collect. That means you've got to create one metric entry inside the collector. Puppet does this in 50 or 60 REST calls. It's trivial to do. So I have these lovely data structures which I pass in some YAML files. These all live in Git, so I push them and update them to Git. Puppet takes over, and it knows how to turn this into configuration. And you end up with a really lovely populated collector with all the metrics that I want to grab in no time at all. So to recap, these are the three bits we've got: SNMP collector, InfluxDB, and Grafana. One of the main requirements we wanted to cover was network resiliency. So the SNMP collector, unlike Influx Data's Telegraph, won't buffer up metrics. It'll just fail to send them, it'll fail to HTTP post them through to Influx. It's not ideal, and you end up with gaps in your graphs like this, where it's flat, there's no data. Grafana will just go and join it, and it looks kind of weird. You want to avoid this as much as possible. So we came across another tool for a stopgap from the open source InfluxDB users and the commercial users. They created this relay agent, which is a Go binary. It has a buffer that you can set the size on. I went with 500 megs because I've got plenty of RAM in my collectors. And what it will do is it'll act as an influx database. The collector will push the information into the front of the relay. The relay will then attempt to relay that out to the remote database. If it can't, it's just got some basic exponential back-off retry logic to empty the buffer when it can. What this means is metrics will keep being collected and buffering up even if there is a network outage. So if one of the fabrics is isolated due to intercapital links being down or power outage in another site, metrics will still be being collected. It also means I can stop the InfluxDB service on our central collector if I want to do a package upgrade. All the collectors then start buffering up their metrics. I do an apt-get upgrade on the central database, start the service again, and the metrics just come flowing back in. It's really, really nice. We had to do some maintenance on the main database machine. It was down for a couple of hours. I was able to, again, stop the service, so they just started buffering up. And with the 500 meg buffers, it was absolutely more than enough to hold that for that couple of hours. Restarted the database, buffers connected back up, and the metrics came flowing in. It was actually pretty cool to watch. So to recap, this is what we've got. Again, there's a collector per fabric that is local to the fabric, connected directly in, so it has the lowest number of dependencies between the devices and the collector. And then we have influx databases on either end of the country. You can actually configure the relay to send to two different places, and it will make sure they get there, so that's really quite nice. The full architecture looks something like this. So Nginx reverse proxy onto Grafana. Grafana talks to Influx. The relays push to Influx. The connectors push to the relays, and the collectors then grab SNMP from the network. We've got a Git repository with all the modules that can install and manage the configuration of Influx, Grafana, and the collectors all sitting underneath. So if I needed to rebuild a connector, it's a 5-minute job with Puppet, and it will just repopulate all the metrics from the YAML files that we keep in Git. Did this work? Well, I think it did. We managed to work with 60-second resolution, though I tried a bunch of others. You're simply limited by the puny CPUs in some network devices. I can't see why you can't put Xeon Ds, low power, high clock cycle in devices, and the newer white box switches are doing this. Would make this a lot easier. We have central storage of metrics, so now I don't have island RRD databases. I can do some cool stuff across databases. So this is one of my favorite dashboards. So it's IX peer. So any peer on the fabric that hasn't requested their data be hidden, you can go in and see the aggregate data for them across every fabric on IX Australia, then split down by fabric. So this is the kind of templated dashboard you can create with Grafana. So I've got a customer or a members drop down, and then a device drop down. So pull up your AS and you can see all your ports and the aggregate across all of them. So you know, okay, I buy 10 gigs of transit nationally, but wow, I'm putting 30 gigs onto peering. That's the value I'm saving, instead of us having to go through and check every RRD. We're also able to look at aggregates across all the IXs. So in this case, you probably just can't see that purple line, but we're regularly hitting over 300 gig nationally across IX Australia. This is excluding New Zealand. We're pretty happy that we've got this insight. So we can tell the value our organisation is providing to the internet community just from being able to centralise and grab more insight from the data we already had. It's 100% puppetised, so Puppet controls everything. If you manually change something on any of the collectors, Puppet will just come through in the next half an hour and put it back. So it's policy enforced. And I add a port for a customer. The index runs every hour or so. It'll come through, walk the device. Oh, there's another port that's up. Great. Add that one and it starts collecting the data for it. So devices, if you've got a 48-port device and only 2 ports up with peers on them, it'll only collect those ports. So I keep the CPU usage down in those devices until they start to fill up. The ad hoc analysis with Grafana is very easy. The Influx QL is very straightforward, and Grafana provides a nice clicky way of going through and pulling out the metrics you want. And we can do lossless upgrades. That's my favourite bit. I can, in the middle of a business day, I put a maintenance page on Grafana, I can do an apt-get upgrade on the Influx box, and 5 minutes later it's done, pull down the maintenance page and all the metrics start flowing in for that 5 minutes. That's my favourite bit. So I do have this for you guys. What I did is last week before, last week maybe. There's now an instance for IX New Zealand. So the same stack that I had in Australia, I was able to stand up in under an hour for IX New Zealand. One collector, one metric store, but exactly the same stack, exactly the same metrics. So you can go in and see the statistics for the IX. You're able to pull out some other bits and pieces with Influx, so I can see the total amount of data used in the last 24 hours. I'm keeping rates, so you do an integral on the rates and you suddenly get a data quantity. And you get some lovely, beautiful graphs out of it. Again, all of these are lovely templated dashboards, so if we ever add another IX, it'll pop up here and I've got very little other work to do. Are there any questions? White shirt down the back. Can you throw the... Yeah, cheers.
Hi, that looks really great. Are there any, you talk about public data, is there any data that will be private to a particular customer or peering? Is there any way of filtering that?
So just like before, peers were able to request that their graphs be hidden. So we're able to hide them within this as well.
All right, thanks.
But they will still remain part of the aggregate. So the summation into the aggregate still exists.
All right, thanks.
Just behind you.
To follow up on this question, are there plans to actually allow members to actually get raw data out of your feed?
Trying to figure out a scalable way of doing that. If there's a demand for it, I'm happy to spend some time to figure out how we can make that data available to members. Again, speak to us, peering at ix.asn.au, or I think peering at ix.nz is also a thing. Contact us and let us know. I'd love to hear some feedback. Anyone else? All right.
So we're a little bit over time, but just before we do go to afternoon tea, I think Ian from Netflix wants to give some stuff away. Is that true? That's true. So if you can go get a cup of tea right now if you want, but if you're not in the room, you don't get it. So what have we got?
So it's a vacuum flask.
A vacuum flask.
And this is a power strip.
Power
which
strip.
takes both USB power and solar power.
Powered by the sun and other power.
That's the Underwood, I think, House of Cards.
Oh, cool. It's a House of Cards one. So it's like evil power. That's awesome. Excellent. So we're going to do this in a totally transparent way where Dave's going to randomly generate a number and then look up on a spreadsheet that only he can see and then say someone's name.
So number 19.
number 90.
And that is Gordon Hooton.
Gordon Hooton, are you here? 3, 2, 1. Okay, another number. It said 54.
Chris Browning.
Chris Browning? Hey, here we go. Excellent. So big thank you to Netflix for that. Thanks, and I will see you, what is it, 10 past now. So we'll 35, 3:35 for a start. Okay, thanks.